16. A metal bar is used to conduct heat. When the temperature at one end is 100 degrees Celsius and at the other is 20 degrees Celsius, heat is transferred at the rate of 16 joules per second. The bar is then stretched uniformly to twice its original length. If again it has ends at 100 degrees Celsius and 20 degrees Celsius, at what rate will the heat be transferred between its ends? Oh, this one's weird. Okay, this equation is essentially equivalent to equation 11.8 in your book. The intensity of energy coming through something is equal to delta, the difference in temperature, divided by, this is essentially the R value. Basically, I just want to solve this just for one substance. We don't have that sum. We can just have it K over L delta T. And then big part of this question is how to interpret the bar is then stretched uniformly to twice its original length. So how are we supposed to interpret that? Does the bar keep the same volume? If it does, then we can say this: volume equals area times L. And we can secondly make A is a function of volume, A equals V over L. And then we can state this: power equals, I'm going to multiply by A, equals K. Let's just go ahead and write it simply, Ka delta T over L. And then I will replace A with this function of volume and length. So when we do that, we assume that the K, the conductivity of the material, and the volume stay the same, but the power that goes through it when the delta T stays the same is inversely proportional to the length squared. So let me write this as a ratio. P2 over P1 is equal to kV delta T over L2 squared divided by kV delta T over L1 squared, which is equal to L1 squared over L2 squared. So if we know P1 was, 16 joules per second, L1 squared over L2 squared, and L2 is 2 L1, then we know that B2 is going to be 1 over 4th times 16 joules per second, which is 4 joules per second. Now, nothing's stopping you from answering that question from here. Once you see that this is a constant and that the power is inversely proportional to the square of the length, and you know the bar is stretched uniformly to twice its length, then it makes sense that it goes from 16 to 4. Number 17, a rigid closed 2-liter container holds 3 moles of an ideal gas. If 200 joules of heat is added, what is the change in the internal energy of the system? Okay, so our ideal gas law and first law of thermodynamics says that delta U is Q plus the work done in shrinking the gas. This problem actually specifies that it is a rigid closed 2-liter container. So what's that tell us? It means that the work done in shrinking the gas is going to be 0. So we know it, and it says 200 joules of heat is added, and the work done shrinking the gas is 0. We can come all the way across here and see that is equal to delta U. So the change in the internal energy of the system is also 200 joules, D. Number 18, a 4-mole ideal gas system undergoes an adiabatic process where it expands and does 20 joules of work on its environment. What is its change in internal energy? Here we have an adiabatic process. In an adiabatic process, I'm going to erase that, we'll say the work, or the heat exchanged is 0. And the work done in shrinking the gas here does work on the environment, so that is going to be minus 20 because it's growing. And so our delta U is minus 20. So that is answer A. All right, number 19, a quantity of monatomic ideal gas expands adiabatically from a volume of 2 liters to 6 liters. If the initial pressure is P sub naught, by what factor does the pressure change? This uses the adiabatic PV curve. We've got a monatomic gas, so the degrees of freedom is 3. The adiabatic PV curve goes PV to the gamma equals constant, where gamma is equal to the degrees of freedom plus 2 divided by degrees of freedom. So in this case, it is 5/3. Now then, the way we'll write that in a full mathematical statement is P sub naught, V sub naught to the 5/3 equals P final, V final to the 5/3. So we will find P final by taking P naught V naught to the 5/3 divided by V final to the 5/3. And we are given, we can even shorten that to P naught times V naught over V final to the 5/3. So this is, we are given the volume, the initial and final volume of 2 and 6 liters. So this is going to be P sub naught times 2 over 6 to the 5/3 power, which is 0.160 times your initial pressure. This question is a little bit oddly worded for the answers. Basically, this answer would be 0.16 rather than 0.16 P sub naught. Number 20 is going to describe an isothermal process. You can tell because it says this thing about maintained at 900 Kelvin. No, I'm wrong. Actually, it started out at a temperature of 300 Kelvin and it went to a temperature of 900 Kelvin. That's interesting. Actually, it's an adiabatic, or not adiabatic, it's isobaric. The pressure remains constant. And so I have written down what is actually going on. The initial and final pressure are 100,000 pascals. The temperature changes, and the volume, do they tell us what the new volume is? No. So what we've got to do is find that new volume based on that pressure, and we can use the ideal gas law for that. What you're going to find is V final is T final over T initial times V initial, which will be 900 over 300 is 3 times 2 is 6 cubic meters. And then to find the work done in shrinking the gas, that will be minus P delta V, which will be 6 minus 2. And also they give us the change in internal energy of the gas is 600,000. So I will go ahead and write that here. 600,000 equals Q minus the work done in growing the gas, which in this case is 100,000 kilopascals times 4. So Q in this case is going to be 600 plus 400 is 1 million, 100, no, 1,000,000 or 1 E6 joules, 1 megajoule, or 10 100,000 joules D. Okay, number 21 says a pound of body fat has an energy content of about 4,100 kilocalories. If a 1,400 kilogram automobile had an equivalent amount of translational kinetic energy, how fast would it be moving? So we're just going to take that pound of body fat, which is 4,100 kilocalories, and convert it into joules. So joules per kilocalorie, we want 4,186 joules per 1 kilocalorie. And that comes out to be about 17.16 megajoules. And then we got this 1,400 kilogram automobile. And we're going to use that in a kinetic energy statement and solve for V. What do we say, 1,400? Yeah, so 1,400 kilograms is going to go on the bottom here, 1,400. We're going to take 2 times 17.16 megajoules E6 and get a velocity of 156.6 meters per second, and converting that into miles per hour, I got 350 miles per hour. Let's see. There we go. I think in this problem, what's going to be easiest for me is just if you want to give the answer in meters per second, give the answer in meters per second, and if you want to give it in miles per hour, give it in miles per hour. And I'll probably let you know in the problem itself whether you have the option to give miles per hour. Otherwise, it'll check it wrong. You can call me and let me know that you answered in a different set of units and you think it should be right, and I'll try to fix it so it accepts it. Okay. On the other hand, if there is some non-SI unit inside the problem, make sure to convert that to SI. Make sure to convert the units so that they're all the same, with the exception being when you're applying something where things can factor out, and you could give, as long as these are absolute pressures, absolute volumes, and absolute temperatures, you can factor things out. Don't do this with relative temperatures and relative pressures, though. Just when you got the absolute, when zero actually means like literally zero, and zero pressure literally means that the particles aren't bouncing against each other. There are situations like gauge pressure and Fahrenheit and Celsius degrees temperature where zero is not the absolute zero. It's just zero temperature is just where water happens to freeze. You can go way below 0 degrees Celsius. And zero pressure just happens to be where your gauge has an equal amount of force in and out. It's equal to atmospheric pressure. But atmospheric pressure is actually 101,300 pascals if you were surrounded by a vacuum. But all I was saying was, when you got a situation like this where units can cancel out, you can use non-SI units like atmospheres or pounds per square inch or temperatures. Well, you still got to use Kelvin pretty much over here for temperatures, but you can use, for volumes, you can use liters or cubic centimeters or milliliters or whatever. And and it works out because the units cancel. All right, it looks like we've finished the practice test. So the actual test is going to be very similar to this. Make sure you can do every problem. It'll be very similar problems with some of the numbers changed around.